My name's
Alex.
My name is Ryan Labs.
My name is Joshua.
And my name is Logan Paul.
So what is radiation? Radiation is from the decay of radioactive elements such as uranium-235 and plutonium-239. Radioactive sources such as this banana right here contain 0.1 microsieverts when consumed.
During a test at Chernobyl's reactor number 4 on April 26, 1986, which is meant to stimulate a station blackout, many workers' oversights caused a disaster which led to 49,000 residents to be evacuated.
What my group and I try to do is we're trying to figure out when radiation levels are safe after a nuclear meltdown.
Okay, so what I'm going to be doing next would be calculating our equation and how I got the equation. And later on you'll see the equation, which is N1 equals NO e to the power of RT, and we're going to just put in our data to find R because we don't know what that is currently. And so our data would be for immediately after the explosion, which at that date of time was 1986. We're going to just set that to T equals 0. And for the other set of data which we have, it would be the time is 2009, which is 23 years after 1986. So that would be our time, and our answer for that, or the level of radiation, would be 2.5 times 10 to the power of negative 6. And then basically we just solve the equation to find R, and once we have R, we just plug in the equation for how long it takes. We plug in R in the equation, and our T would be 31 because that's how many years after 1968. So our equation is N1 equals NO e to the power of RT, where N1 is the answer, NO is our initial amount, E is E, and R is rate, and T is time. So we already have we already collected some data, and our data for our answer was 2.5 times 10 to the power of negative 6 equals to our initial amount 0.125 times e to the power of R, which you don't know, that's what we're solving for this time, to times time, which is 23 in this case. And so what we do first is we divide by our initial amount to both sides, and we would get 2 times 10 to the power of negative 5 equals to e to the power of R times 23. Then what we do is we want to move these over by properties of log, so we ln both sides, and the ln of e, and the ln of e is 1, so this would disappear later on, and we would get ln of 2 times 10 to the power of negative 5 equals to 23R. And then after that is we just divide 23 by both sides, and we get R equals to ln of 2 times 10 to the power of negative 5 divided by 23 equals to approximately negative 0.47. So now that we have R, we just have to re-put in the equation, and 31 in this case stands for 2017 because our original date was, it was 1968, and we just set that as T equals 0. And the other time when I used 23, we were talking about the data collected from 2009. So you would just add 8 to this, which is add 8 to both, which is you would just get 31. Yeah. So that's how we got our time is 31, and then you just plug all this into the calculator and you get around 0.05.
Based on our calculations, Chernobyl today should have been at a 0.05 microsievert level, which is basically safe.
We were wrong.
Very wrong.
So the reason why we were wrong was because our calculations did not include every single factor, therefore a part of it was incorrect. And if you look at an actual site, which is like the official site for Chernobyl, it will tell you the official amount, which if you average it is around 1.748.